Okay, so I'm over on the portal. I've opened up a terminal and I've also um, uploaded the plastic.step file um, into my directory. Okay, I made a app. Let me go back here. I made an app5 directory. So I do pwd, it shows me where I am. So I'm in work classes ME461, and then I made a directory make dir app5, and then I'm going to go into app5 and I've uploaded the plastic.step file, and we also need the environment variable, which I'm actually going to copy. You can download it and go through that same process, but I'm also going to copy this. So this says copy one directory back. So this goes into the 461 directory, and then I'm going to go into the app4, and then I have that file, that abacus. I hit tab a bunch of times and it shows me things with the letter A. And then I have the abacus v6.environment file I want to get. Okay, I'm going to copy that here. So this says copy one directory back, go into app4, and copy the file abacus underscore v6.env, and then copy that to here. The dot means right here, which I'm already in app5. So that takes us here, and then when I do an ls, you see both of those files exist. Okay, now we can module load abacus and vgl run abacus cae. All right, and we're at this location. Again, I like to go in there and control my graphics options just to make it a white background. Okay, and then I'm going to import the part. File, import part, say step file. So grab that plastic.step, say OK. You'll see in the packet that's applied that we're going to scale this. So I'm going to do it quickly here. Multiply this by 0.001. This takes it into meters. I like to work in kilograms, meters, seconds. Say OK. And there we have three different components for our part. At this point, we can go into properties and create some material properties. We're going to go into the density. We're going to make a steel, and density is going to be 7,800 kilograms per meter cubed. The elasticity, we're going to have a Young's modulus of 200 e to the 9 and Poisson's ratio of 0.3. Okay, that's the steel linear. Actually, we should probably rename this. Well, it's okay, we can rename the next one. We're going to create a new material and we'll call that steel nonlinear. So steel nonlinear, linear. And density is the same, 7,800. Elasticity is going to be the same thing, 200 e to the 9, Poisson's ratio of 0.3. But now we're going to add in a new feature here. So we're going to add in, basically what you can do in Abacus is you can add all these different material models onto it. And so some of them add, it's almost like tacking additional terms on here it's pretty neat how they did it, actually. But it's actually attaching different terms and different mechanics, or mechanisms, if you will, onto your material model. So here we're going to add plasticity, and we're going to go with the simple plastic model. And this is the yield source that I talked about in the introduction, where you can define the endpoints of where you are. So the initial yield point is we're going to put at 0 yield, it's going to be 300 e to the 6, 300 megapascals at a plastic strain at 0. That's the initial yield spot. And then there's something called plastic strain that we accumulate. So this tells us about how much, what's called hardening. So the slope of that curve, after we hit elastic and then it goes, starts to yield, what is that slope on the plastic portion? So we can do that by, hold the right mouse button down and do row after. And then we'll add a little bit of hardening here. So we'll say 310 e to the 6th, 310 megapascals. And that's going to happen at a plastic strain of 0.05. So now we can say OK to that, and we have materials. We're then going to create two sections. Section 1 will be our elastic one, so we'll give that just a regular steel, and then we'll create another one which will be the steel nonlinear. And that one will have the steel nonlinear properties, and then we'll assign these parts to the sections. So this steel bar is the one we're going to try to bend plastically, and so we'll select this and say give that to the nonlinear, and then for the other parts are basically the molds or the anvil, and we're going to select that just to be elastic, so we don't have to worry about the plasticity there, although we could leave it on if we wanted to, but you probably want some hardened steel, much harder than the thing you're trying to bend, right? So you'd have to do that. Okay, so everything is green, which means everything has a material property assigned to it. Now we can go into the assembly, and this is easy because we'll select all these items, say OK. If we'd like, we can actually color this. I'm not sure if I've shown this option yet, but you can go up to, your layout might be a little different, but if you go up to this palette, you can color by, say, materials. And there you can see we have the same materials on two of the components, and one is the nonlinear one. Okay, our next item is go to the step module. We're still in the static regime, so we'll go with a static step. Here we're going to select a couple things. First is we're going to specify the dissipated energy fraction. Okay, so we're going to add a little bit of automatic stabilization. Remember, this basically affects by taking out some energy from the equations by multiplying it by some factor. Here, 0.0002, so something small factor there. We can track this in the energy plots and the history output that we looked at before, and the reason we're doing this is because we're going to have contact in this, and sometimes contact can lead to problems, so here we're going to try to add some stabilization to that. The other thing we want to do is, I like to do the incrementation. Helps with stability as well as just plotting the solution procedure. And in this case, we're going to select 0.001 and make the maximum 0.05. All right, next we're going to define the interactions, and for that we're going to create an interaction. In the packet we actually create the property first. It's kind of like a material model, so we can do that. Create the interaction property. We're just going to give a friction, a tangential behavior. We're going to use the penalty friction of 0.1. Say OK to that. Now we're going to go to create interaction, and we'll go with the surface to surface. Say continue, and it asks for you to select the surfaces. So we'll select this top surface first. Okay. Again, I previously talked about the terms master and slave. I choose to use primary and secondary. So this would be the primary surface that we're selecting. And then it asks for the secondary. And so we will select the underneath. This anvil is going to, so we'll select the bottom of the indenter. So I'm going to shift. So it's going to be actually we have to select surface first, so it's a surface type, and then we say done, and then we can say yeah, this is going to be surface to surface. Again, there's lots of node, you can do node to surface, surface to surface. There's lots of different contact algorithms out there, but we can take the default here, and it already comes up with our interaction property that was defined. So we can say OK to that, and we'll see those squares, those yellow squares pop up. Let's do another one. So another surface to surface, and in this case we're going to do the bottom of the bar and the top of the support contact. Say done, and then we can accept this also. It's already populated. Okay, so there we have our contact defined. This is a good spot to do a file save as. I'm going to call this APP5. Okay, our next step is to go into the load. We're going to apply the boundary conditions. We're going to start by having introducing some symmetry conditions. So here we're going to align, let's align our part like this. Okay, so X, Y, Z. Okay, and then what we'll do is we're going to create a boundary condition. We'll go to displacement rotation. There are a couple ways to actually do the symmetry condition. I just manually created it here. So you could go to select the displacement, and you're going to hold down the shift button, select these three faces. So we're actually going to rotate it mirror it over the x-axis. So it's a symmetry condition on this side. All right, so we'll say done here. And then because it's a symmetry, it can't go in X, all right, but it can go in Y and it could go in Z, but it can't move out of plane in X. So that X value is going to be 0. Okay, and we should see something like that. All right, we're going to do that also for the other side. So we want to mirror this over the Y, or I guess it would be mirror on the Z as well. So we're going to do this one more time. Continue, select these faces, and say done. And in that case, we want to, it can't move in the Z direction. Okay, say okay. The next option is we'll add the fixed constraint on the support. So let's rotate this around. So what we'll do is we'll select that face, say done. We're going to keep that fixed, so nothing in the X, Y, or Z. Say OK. And then the final one will be pushing the indenter another displacement on the top face. Say done. And that's going to be in the Y direction of negative 0.035. Say OK. And there's our boundary conditions. We can now move on to the meshing. So we'll seed the part. Of course, we get that error about the dependent instances. So on the bar part, we'll seed and we'll go with 0.002. Apply. Pretty fine mesh there. And then mesh that. Looks pretty good. Go on to the indenter, and we'll go with 0.003. Say yes. And finally, we'll go here to also 0.003. Okay, so if we look at there's our mesh, looks pretty good. Pretty surprised we were able to get hexahedral meshes out of this curved geometry, so that's pretty good. All right, and then next we will go to the job. We go ahead and create that job 1, take all these defaults, go to the manager, and we can do a data check. And that check successfully ran, so we can then submit the job. All right, that just takes a couple minutes. Let's end it here. In the next video, we'll do the post-processing.